All right, today we're going to be talking about the California fire climate, which is chapter 2 of Fire in California's Ecosystems. I did the same thing as chapter 1 where I summarized the entire chapter in a 1-minute video. I'll play that really quickly, and then afterwards we can go through it line by line to just dive in deeper and just better our understanding about the California fire climate. Wildfire is a natural part of the California ecosystem because we have what you could call a fire climate. Most of our precipitation occurs in winter. During summer, there is very little rain and warmer temperatures, so we have more moisture leaving the plants due to transpiration than what is being absorbed. With drier fuels, it's easier for fires to start and spread. One thing working in our favor is the Sierra snowpack, which acts as a delayed release of moisture, slowly melting as we get into fire season. One thing working against us is that right at the peak of fire season is when California sees the most lightning, which can ignite fires. However, most fires are started by humans, and while fire suppression is necessary to protect life and property, it leads to the accumulation of fuels and promotes more burning when fire danger is highest. Let's start out by diving into the first line here. Wildfire is a natural part of the California ecosystem because we have what you could call a fire climate. Now, I think the key words here are natural part and fire climate. So what I mean when I say wildfire is a natural part of the California ecosystem is, well, humans certainly do have an influence on fire today. We start a lot of fires, we suppress the fires, we lead to fuel accumulation, all those sorts of things that we'll talk about later. But when I say natural part, I'm emphasizing that wildfire has always been a part of California. At least it has for thousands, if not millions of years. And that's why a lot of our vegetation, even some of our animals, have adapted to fire. Some of them actually can't even survive without fire, and a lot of the problems that we see in our ecosystems today is not because of too much wildfire, but actually too little, which is kind of interesting. And the reason that our plants, some of our animals, have adapted to wildfire is in large part because California has a fire climate, which is what we're going to be diving into throughout the rest of this video. One of the key aspects that leads to California's fire climate is most of our precipitation occurs in winter. During summer, there's very little rain and warmer temperatures, so we have more moisture leaving the plants due to transpiration than what is being absorbed. With drier fuels, it's easier for fires to start and spread. Let's think about this section as precipitation versus transpiration. So in California, most of our precipitation occurs in winter. That's because there's a larger temperature contrast from the equator to the poles, so the jet stream is strengthened. There's just basically a bigger gradient, and it's the jet stream that steers storms either into California or during summer, the jet stream moves north and we don't see as many storms. So when that happens, we get these cold fronts that go through California, and our rainfall isn't evenly distributed. Before these fronts arrive, a lot of surfers know this because the southerly winds kind of ruin the surf before a storm comes in. But we have southwesterly winds. And then what that's going to do is those winds are going to take a lot of the moisture that's coming in from the storm, and it bumps up into our coastal mountains, especially the ones facing southwest or roughly that direction. So then this moist air is lifted up, it creates clouds. A lot of that moisture is then squeezed out in the form of rain on the windward side of the slopes. But then as the wind goes over those mountains, on the back end, almost like a sponge, most of the moisture has already been squeezed out, so on the back end it's a lot drier, and you get what's called a rain shadow effect. So that talks about how our precipitation isn't evenly distributed in space, but it's also not evenly distributed in time. Because of what I was talking about the movement of the jet stream, most of those storms that bring most of our rain, that's going to happen during winter. Now during summer, there is some rain that moves into California, mostly due to the North American monsoon, but that's more in our deserts. Eastern Sierra brings some summertime thunderstorms, but it's usually not enough rain to actually bring moisture back into our soils, so it doesn't really play into fire season all that much. What does play into fire season is the fact that we don't have much rain during summer. So during winter, you could think of our soils and our plants just absorbing all of this moisture. It'd be very hard to start a fire at that time. Versus in summer, the temperatures start to ramp up, and temperature is directly proportional or has a large impact on what's called transpiration, which is basically, think of the plants as pumping moisture out of the soils and just getting drier and drier. Then we'll just simplify this. Just think of like a campfire. If you have two logs, you have a moist log and a dry log, and you're trying to start that campfire. It's getting late, you're trying to make some s'mores or something. It's going to be a lot harder to start the fire with the moist log than the dry log. And then the dry log is also going to burn hotter and faster. So that's basically what happens in California, is in the summer, our vegetation dries out. So it's not only easier for fires to start, but then they'll spread rapidly once they do start. So basically, conditions get drier during summer, and that makes wildfire more likely. Now, one thing working for us is the Sierra snowpack, which acts as a delayed release of moisture, slowly melting as we get into fire season. One thing working against us is that right at the peak of fire season is when California sees the most lightning, which can ignite fires. So let's dive into that first sentence a bit more. That's about the Sierra snowpack. You think about most of the rain in California is going to fall between November and March. So then as you get into April and May, in the lower elevations, you're already going to start drying out unless there's some miraculous late season rain, but usually that doesn't make a huge difference. But up in the Sierra, we have what we consider the largest reservoir in California. You could think of it just as a storage of water, but it's in the form of snow. So that's mostly going to be melting during April and May, and as it melts, it slowly trickles into our soils. What's in the soil goes into the plants, and that's pretty important up in the Sierra because we have a lot of fuel up there. There's millions of dead trees because of bark beetles, but that's maybe something for another video. But basically, it's delaying the drying out of our forests up in the Sierra, and that's good for wildfire because the drier things are, the easier it is for fires to start and spread. Now let's look at that second sentence, which is talking about lightning. Most of the lightning is going to occur in the higher elevations, so we have something working for us in the mountains, kind of reducing wildfire activity, which is the snowmelt. But then lightning can also lead to more activity because obviously lightning can start fires. Now, between 1985 and 2000, there was 1 million lightning strikes in California. Half of those occurred in the southeast deserts, but then you also get a lot on the eastern crest of the Sierra and then the peninsular ranges in Southern California. Interestingly, I love this fact, Central Coast has the lowest amount of lightning in the entire United States, which is a pretty interesting fact there. And that actually has impacts on how the plants would have evolved throughout thousands of years. And this ties back into California having a fire climate. Think about before humans, lightning was the thing making most of the fires. So how often you would have lightning fires would determine how those plants adapt to lightning. So on the Central Coast, we have a lot of chaparral, which kind of is used to and has adapted to a fire return interval. So the space between fires of about 50 years. So if there's fire every 5 years, that's not what the plants are used to. So then it could, for example, wipe out the chaparral. Whereas over a 50-year time span, some of the chaparral plants have time to build up their seed banks. They have time to build up reserves in their burrows. So then when a fire comes through, they can just re-sprout immediately. And it doesn't hurt them, it actually helps them in some ways. Whereas up in the Sierra, where there's more lightning, in part because of the North American monsoon, or you could just think afternoon thunderstorms that are mostly between or actually right around the peak of fire season. So with more lightning, there'd be more fires starting historically in California. So the plants would be adapted to a fire return interval of maybe 5 to 15 years. So think of like giant sequoias in this case, where they've been adapted to kind of be in an ecosystem where there's not many plants around them because they're used to those fires frequently coming through, clearing things out. And then they have fire-resistant bark. They engage in self-pruning, where they drop their lower branches. So if a surface fire comes through, it doesn't catch the whole tree on fire. So that is what they're used to. But if then we do fire suppression and it allows a lot of fuels to build up, that's no longer what the giant sequoia is used to surviving in. So you have a massive fire that comes through every 40 years, and now it overwhelms the tree's natural defenses, like its fire-resistant bark or its self-pruning. And instead of just a surface fire kind of clearing out competition and helping the giant sequoia, the fire overwhelms the giant sequoia and basically just can destroy an entire grove. So hopefully I didn't go too off course right there. I'm trying to tie in the snowpack, lightning, with the fact that we have a fire climate in California, and really diving into how this would have worked historically and how these plants have adapted. But a key thing I do also need to point out is I've talked about how lightning can start fires, but most fires are started by humans. So let's look at that part of the video where I say, however, most fires are started by humans, and while fire suppression is necessary to protect life and property, it leads to the accumulation of fuels and promotes more burning when fire danger is highest. The first part of this is pretty self-explanatory, and we've already kind of talked about it, so I'm not going to spend too much time on it, but it's talking about the accumulation of fuels, where if you normally have fires come through an area, let's say up in the Sierra every 5 to 15 years, then that's what the ecosystem would be used to. But if you suppress fires when they happen, which you kind of have to do to protect life and property, we obviously can't just have fires running rampant throughout California. If you suppress the fires, then the fire doesn't go through the area, it doesn't clear out those fuels, and then those fuels just continue to grow. But why is this a bad thing? So this is a bad thing because California has a fire climate, we dry out every summer. We also have droughts that'll last for years at a time, so eventually all those fuels are going to dry out, and then when a fire comes through that we can't suppress, it ends up being much worse, much more extreme than if we had just allowed little surface fires to come through, let's say, every 10 years. Now this sort of ties into the last part as well, about how this promotes more burning when fire danger is highest, but I think there's 3 charts that really break that down even better. So in this first chart, the y-axis is probability of active fire spread, and then on the x-axis we have the fire climate going from moist to dry. And then you see those 2 lines. You could think of the top one as fire in California where there is no suppression. It's almost like looking at fire in the past, before humans were here, before we were suppressing fires, and what that probability of active fire spread would have been like. And then that bottom line is closer to what fire in California is like today, where we are suppressing fires. Now there's 3 things that I want to point out on this chart. First is that those 2 lines that represent active fire spread don't go to the corner of the chart, and that's because there's some days that just have so much moisture in the air that you're not going to have a fire whether you are suppressing them or you aren't. There's just too much moisture, fire is not going to start and spread. Second thing I want to point out is that both of the lines are going up and then they peak at the end of the graph. And that's just saying that the probability of fire, it's more likely to have fire the drier things get. I don't need to make that more complicated, it's that simple. If it's drier, it's more likely you're going to have fire. Now the last thing is a little more nuanced, a little more difficult to see at first, but that bottom line, which represents fire today, so where we are suppressing, it's kind of shifted over to the right a little bit. You notice more of the area under that curve is going to be in that drier climate. And you could think about how this works in the real world. So let's say a fire starts and it's 70 degrees out and there's 40% relative humidity. It's kind of a normal day. Well, the firemen are going to be able to get to that fire, put it out immediately, so then there's not going to be that much fire spread that day. That'd be somewhere like in the middle of the graph. However, let's say a fire starts and it's 90 degrees, relative humidity is 7%, super hot, super dry. The crews try to get out there, but it's so hot and dry that the fire just takes off, it's out of control. So then there's more fire spread that day. What that's basically saying is we're better at suppressing fires when it's normal conditions, so there's less fire activity on those days. And then it shifts more of that burning to the right-hand side of the graph. All right, if that one got a little complicated at the end there, this next chart is very simple. It's just percent of time on the y-axis and then our same fire climate on the x-axis. And it's a perfect normal distribution. And there's no tricks here. This is basically just saying if you look at climate over time, most days by definition are going to be normal or close to the average, and you're going to have fewer days that are either extremely moist or extremely dry. It's just a classic bell curve. This final chart wraps everything together, and you could think of it as multiplying the first 2 charts together. So the first thing we'll do is look at that solid line, which represents no fire control. And there's 2 things I want to point out. The first one is that it still looks like the bell curve, and it's for a pretty simple reason, and that's just if you have more days that are spent in that normal fire climate, then it's just more likely that you have fire on one of those days because it just takes up more of the time. Now what's maybe a little less intuitive is why the curve comes down at the end. If you think back to the first chart, you would think, well, wouldn't you still expect more fire as things get drier? But it actually looks like you have less area burned as things get drier. Doesn't really make sense at first. Remember, this is in our no fire suppression scenario. Now, the reason for that is because you have so much fuel that's burned during the normal time that there's just less fuel left over during the times where the conditions are very extreme. So there's two aspects going on there. One is that a lot of the fuels have been cleared out, but then the other aspect is that there's also just fewer days that are extremely dry. So it comes down. But you notice the other curve, which is the dashed line, which represents where there is fire suppression, really comes up at the drier part of the curve. Now, why is that? First part is because they're suppressing all the fires that are happening under normal conditions because it's easier to suppress those fires. But then it really jumps up during the dry conditions. One, because that's the only time where it gets out of control enough to where we can't suppress it, but also because the fuels haven't been burnt out during the normal conditions, so there's more fuel left over for when the climate is most extreme. If that got a little confusing at the end there, I'll just try to do a quick summary of what we've talked about. Basically, California has a fire climate, and that's why even if humans weren't here, we would still have wildfires just like we did for thousands of years. And the big part of the reason for that is we have a Mediterranean climate where we have wet winters and dry summers. So at the hottest part of the year, it's also the driest part of the year, which I've lived in California my whole life. I thought that was how most of the world worked, but most of the world is actually wettest during summer. So at the hottest part of the year, it's the wettest part of the year, so that kind of cancels each other out in terms of wildfire. Opposite for California, we're hot and dry at the same time. Fuels dry out, makes fire a lot more likely, and at the same time, that's also when we have the most lightning. But one thing that works in our favor up in those higher elevations where we have the most lightning is we also have the snowpack, which slowly melts as we get into fire season, bringing more moisture into our fuels and kind of delaying the drying out of a lot of our forests up there. So with the lightning, that can ignite some fires, but as we talked about, most fires are started by humans. And then when fires do start, we suppress them because obviously we can't just let them run wild and go through cities or towns and put lives and property at risk. But the downside to that is then those fuels aren't being cleared out. So then those fuels accumulate, and we can also have much better success in suppressing those fires on normal days. So we're basically just kicking the can down the road, or as the textbook said, robbing Peter to pay Paul. We're basically just kicking the can down the road with all of those fuels until the day where it's too hot, too dry, too windy to be able to suppress the fire, and then we have an extreme blaze. Now, that obviously has dangers to life and property, so it kind of, the reason that we were not allowing fire in the first place kind of comes back with a vengeance, but it's also not what's best for the California ecosystem. As I mentioned, a lot of our plants here have adapted with fire for thousands of years. So when we tilt the ecosystem out of balance, then you can end up in a situation where it overwhelms the natural defenses and adaptations that these plants have built up over thousands of years. Now with that as well, it's a very complicated problem. I'm not going to pretend to have all the answers, and there's other things that we value as well. So hearing this video might say, oh, we should just allow more fires to happen, more burning. But we also like air quality. We also don't want a bunch of soil erosion, so we want those fuels intact. There's lots of different things that we have to balance, and I'm still learning a lot about that, so that's why I'm going through this textbook, and I'll continue to share what I learn with you along the way. So thanks for watching. Hopefully you learned something, and till next time.